questions. So our next speaker is Laurel Dunn, who is a PhD candidate in civil engineering at University of California at Berkeley. She specializes in grid data, risk assessment, and decision analysis in power systems. Her work deals with knowledge transfer and with facilitating partnerships necessary to deploy next generation analytical tools and at utilities. And so Laurel's paper that she's going to present here is the Bayesian Hierarchical Methods for Modeling Electrical Grid Component Failures. And we will have this to be presented as a recording. So we're going to play the recording. So I would ask the host to do that, to get that ready. And I just want to say here, as we're starting out, and I know we are getting a little bit towards the end here, I really recommend staying for Laurel's presentation and the topic of this paper, which is really trying to answer some of the hard questions of like, how do we get the data about failure probabilities from power systems? So, and modeling the probabilities of component failures. So, is it possible, could we get the recording ready, please? Hello? All right, okay, great, perfect. All right, so then we will watch the recording. Okay. And also I want to say, and Laurel is also here to answer questions. So she's here in the session. So we will have questions once the video is also over. Okay, yeah, we can start the video then.
Good morning. My name is Laurel Dunn. I'm calling in from Berkeley, California, and I'll be presenting today with my co-author, Mathilde Badoual. Our work deals with generating failure models or fragility curves that describe the probability that grid components will fail when exposed to certain stress conditions. To cite a couple examples, these fragility curves could examine the probability that a pole will fail under high wind speed conditions, or that a transformer could overheat under heavy loading. More generally, fragility curves relate stress conditions on the grid to the probability that a component will fail. Failure probabilities are, of course, constrained to be between 0 and 1, and are expressed as some parametric function of the stress conditions x. In our work, we use a logistic function, though you'll see other functional forms reported in the literature as well. Here is a graphical representation of a fragility curve. On the x-axis is the stress condition, in this case wind speed, and the y-axis is the probability of failure. This figure compares 3 fragility curves for different proposed designs, in this case of a roof, characterizing the relative vulnerability of each design to high wind speed conditions. You could consider a similar example in power systems, might look at the relative vulnerability of wood versus concrete poles. The parameters of each failure model would typically be estimated using observational failure data. The challenge is that failures are rarely observed in operation. This is because the system is designed to be robust against failure under most conditions. Components can also have incredibly long operating lifetimes, often on the order of decades. And preventative maintenance schedules aim to replace components before they actually fail. What this means is that failures may not necessarily be observed in operation. To get around this fact, failure data are often supplemented using accelerated life test data, which are generated by subjecting components to stress conditions in a laboratory environment. The fundamental limitation of using laboratory data to characterize the vulnerability of a real-world system is that the laboratory environment lacks fidelity. In practice, we see risk factors that may be compounding and don't necessarily come in isolation of one another. Manufacturing defects can lead to differences in performance, and complicated degradation processes can impact the state of health and performance of components over time. Many of the risk scenarios that we care most about are incredibly challenging, if not impossible, to mimic in a laboratory environment. Consider, for example, earthquakes or fires. And it's not unprecedented for us to see components failing in operation due to failure modes that were not previously understood. It's impossible to mimic these failures in a laboratory environment. There is a body of literature looking at generating fragility curves using empirical failure data observed during earthquakes and hurricanes. A conventional approach would be to use methods like maximum likelihood estimation to approximate the parameters of a fragility curve for a system overall. However, there have also been studies showing that failure probabilities for individual components vary depending on characteristics like state of health, age, and siting. The main contribution of our work is to develop a framework for quantifying uncertainty and bias in the failure parameters of these fragility curves, in light of the fact that the empirical data available to us may be sparse, may be associated with health conditions that are not directly observable to us, and in light of the fact that the system as a whole is highly heterogeneous, and that individual components may have very different operating characteristics and stress exposure. We do this using a probabilistic framework that relies on Bayesian hierarchical models to characterize the probability that the parameters of this failure model will take on a particular value.
To characterize those fragility curves, we use Bayesian hierarchical models. This choice is motivated by three main reasons. The first one is that the data available is sparse and rare. The second point is that failures has been studied and we have access to physically informed models. And the third point is that characterizing failures probability is necessary for grid operators and is part of the decision-making process. So it is important to provide confidence intervals in the information we deduce. But what is Bayesian hierarchical model? They characterize the relationship between inputs and outputs where the parameters are random variables. So they have inherently the uncertainty. In the figure 1, we explain the one layer for the Bayesian hierarchical model. We have X is the input, Y is the output, M theta is the model, and theta are the parameters of the model that are represented as random variables. And another layer of the Bayesian hierarchical model could be that this distribution, P of theta, is also characterized by other parameters. So the goal here is to identify the distribution theta of the model P of theta that relates the input X to the output Y. And this value can also be written as P of theta knowing X and Y. It's also known as the posterior distribution given the data X and Y. And using the Bayesian theorem, we have the following relationship, where P of theta here is the prior distribution of the parameter theta. P of X and Y knowing theta is the likelihood function. Also, we can also describe it as the probability of observing the data X and Y given a particular estimate of the parameter. And finally, P of X and Y. So it's the likelihood of observing the data independent of the parameter. This quantity is important. It's known as the normalizing constant and generally cannot be computed analytically. So instead, we use Markov chain Monte Carlo method to compute the posterior numerically. To choose the model M, we use the common form of fragility curves used by reliability engineers. So they describe the probability of failure of a component when exposed to certain environmental conditions in X. So we have in equation 2 the fragility curve, where P here is the dimension of environmental conditions that will impact the failure probability. So for example, one dimension can be winds, another one can be precipitation. So the failure of one component is then a Bernoulli trial with the probability g of theta of x. Assuming that all the components have the same fragility curves, the number of failures over all the grid follows a binomial law. And if we use the Poisson limit theorem, we have that the probability of having y failures during the time of the observation is a Poisson process, here in equation 3. Then we deduce the model m of theta, which is the Poisson process with probability and multiply by
the fragility curve.
With that context on our underlying approach, I am going to talk about our analysis methods. At a high level, our objective is to fit and evaluate this Bayesian hierarchical model. We do this by generating data in simulation using failure parameters that are known to us. Given the data that we generate, we then estimate the parameters of these failure models, of candidate failure models, and select the model that is most appropriate. We feed this model into a risk assessment framework that informs an upgrade policy. We then compare the characteristics of the selected model and the upgrade policy against the true distribution that was used to generate the data in the first place. This is our model evaluation technique. Next, I'll describe our data generation process. First, we generate environmental stress data, including wind speed, precipitation, and temperature, by fitting parametric distributions to weather data recorded at a site in Northern California. As Mathilde mentioned, the Bayesian hierarchical framework assumes that the parameters of these failure models are themselves random variables. And we use a similar concept in generating the data. We specify parameter distributions characterized by some mean and some coefficient of variation, from which you can arrive at the variance. And we look at fleets of components that are increasingly robust to a failure under given environmental conditions. And we look at fleets of components that have varying degrees of heterogeneity in the failure parameters between one component and another. For example, in a homogeneous case, the coefficient of variation is equal to 0, and the failure parameters are assumed to be the same for all components on the system. We then sample parameter values from these distributions in order to generate fragility curves for each component on the system. We simulate failures that would occur based on these probability distributions over 10 years in operation with a time step of 1 hour. Next, I'm going to talk about our results. On the y-axis here, we show the failure parameter alpha, which describes vulnerability to wind speed conditions. In orange, we show the range and distribution of this parameter learned using the Bayesian hierarchical model. And in green, we compare against the maximum likelihood estimate. Blue shows the full range and distribution of values that we specified. This is the true distribution. Now I want to highlight two results. First, we can see that both the Bayesian hierarchical model and the maximum likelihood estimates systematically underestimate the mean compared with the true distribution. Now the reason for this is that, as I've mentioned, the system is designed to be robust to failure under most of the wind speed conditions that are observed. This means that most of the failures we do see are among those components that were already more vulnerable to fail. So there's a systematic bias in the failures that we observe. Second, I want to point out that our method significantly underestimates the variability relative to the true distribution. The reason for this is that failure data are sparse. Ultimately, the main objective behind generating fragility curves is to characterize the risk exposure of the system. Risk assessment algorithms can be used to inform upgrade policies that a decision maker may follow to achieve some targeted risk reduction. Here we compare our model against the true model using a decision analysis framework where the objective is to upgrade the components on the system in such a way that minimizes the number of components needed to achieve a targeted risk reduction goal. Here we specify this goal by defining some damage thresholds, delta, and constraining the system, the target distribution, that is, so that the probability of exceeding a damage state in excess of delta stays below some acceptable risk tolerance, epsilon. We can do this by capitalizing on the range and distribution of parameter values that describe the relative vulnerability of components on the system to a particular stress condition. This figure shows that by identifying the components that are most vulnerable to fail under less severe stress conditions, we can minimize the number of components that need to be upgraded in order to achieve this targeted risk reduction goal. This figure shows upgrade policies informed by the true model, the Bayesian Hierarchical Model, and the maximum likelihood estimates. The y-axis describes the fraction of components that would need to be upgraded in each setting. The system on the far left has a mean failure parameter of 65 meters per second. And you can see that it is severely underbuilt given the environmental conditions and the risk tolerance that we have specified. This means that a large portion of the components end up being targeted for upgrade. The system on the far right, on the other hand, is very robust to the conditions. And we see a much smaller portion of components being upgraded. As we discussed previously, the Bayesian hierarchical models and maximum likelihood estimates tend to underestimate the variability in component performance, which means that both models tend to target more components for upgrade than is really necessary, given the true model. With that, we have run out of time, and so I'm not going to talk about this slide, but my understanding is that this video will be available on the PSCC website. I welcome you to watch it again, and please do get in touch if you have any questions or if you have ideas for future work.
All right, thank you so much. This was, thanks for preparing this presentation, Laurel. And yes, the video will be available. Do we have any questions for Laurel as we are about to end here?
I see a question from Carlton. So Carlton asks, the fragility curves attributed with FEMA's HAZUS tool are a standard. And just to comment on those curves, my understanding is that they're basically founded on the same concepts, the same type of model, but they give uniform failure properties and failure parameters for the system overall. In expectation, this is probably fine, but in practice, there are some components that are likely at much higher risk of failure than others. So understanding the range and variability can be important for some applications.
Cool. Yeah, so there's another question here also from Patrick Pansitisi. In the case of actual data on the operational system, we try to use information on survivors to improve estimations using Kaplan-Meier estimator. Is that compatible with your approach?
I'm not familiar with this concept, so I don't know. I will investigate that.
All right. Yeah, maybe something to look for. All right. So yeah, I guess then I'm just trying to see if there are any more questions here. I don't think so. So I was just curious, actually, and you might have already mentioned this, but this. So you were mentioning that the. I mean, you were seeing that the variability that is severely underestimated.
Mm-hmm.
And what was the reason for that? Do you have any good explanation?
Sure. So to understand the full variability, you need to see failures that are happening kind of across the full domain of risk scenarios. And until you see a realization of those really severe risk scenarios, you're not necessarily able to characterize the probability that a failure will happen in that space. So simply because the really extreme wind speed conditions, for example, aren't that common to see, it becomes difficult to characterize the probability of failure during those types of events.
And do you think your method is providing kind of a path forward to addressing that challenge?
Yeah, so so our results underestimate this variability. One of the reasons for that is that we used an uninformed prior in our Bayesian formulation. One way to improve on that would be to draw on expert judgments or like accelerated life test data that would allow you to extrapolate into those more severe conditions. So the synthesis between domain expertise and laboratory test data with empirical data using this Bayesian formulation could potentially help us to better understand the full range of what's possible.
Okay, that's great. Good to hear. Well, so thank you very, very much for your presentation here and also for the questions. And thank you to everyone who is here and for everyone who is staying with us all the way until now. It's really my fault that this went over time. So I am glad that many of you were able to be here also all the way until here. With that, I would like to close the session. Thank all our speakers again very much for attending and for having such a lively discussion, to all the attendees also for all your questions. And with that, I think we can close the session for now. Thank you very much.